A number of you have expressed difficulty with finding the domain of a function when you're actually given the equation of that particular function. So I want to kind of walk through some examples, but before we do that, I want to kind of give you a little bit of background information. It's important to remember that the domain is the x values that you can use in the function. So the way I define it is it's the usable x values for a given function. And in most cases with a function, we assume that the domain is going to be all real numbers, that we can use any number that we can possibly think of within our number system that's on the number line. So that's from negative infinity to positive infinity. But there are two possible restrictions. The first restriction is if you are going to be dividing by 0, that is a problem. Mathematically, that is not possible. And so you have to pay attention to whether or not your denominator, if you have a fractional or a rational function, you have to pay attention to whether there is a variable in the denominator or the bottom half. And if there is a variable in the denominator of the function, then you have to avoid any value that's going to cause that denominator to be 0. And I'll show you how to do that in just a minute. The other restriction is that you cannot take like the square root or the fourth root or the sixth root of a negative value. Hopefully you remember, and let me see if I can give you some examples here from earlier algebra, that, you know, if you try to take, say, the square root of negative 4, that's really the square root of negative 1 times 4, and the square root of negative 1 times the square root of 4. Remember, by definition, the square root of negative 1 is the imaginary unit, and the square root of 4 would be 2. So you end up with an imaginary number. Well, if it's imaginary, you can't see it or graph it or plot it on your grid. So you have to avoid having a negative number under an even indexed root. Now, what we mean by an even indexed root, again, is like a square root or a fourth root or a sixth root. Now, if you have something like, for example, the cube root of, say, negative 8, we can find the cube root. Cube 3 is odd, so that would be negative 2, because negative 2 raised to the third power would give you negative 8. So you only have to worry about it if it's an even indexed root. Now, again, there's a variety of ways you can do these problems. You can do them visually if you have a graph. Primarily, I believe in Newton, they're giving you the equations. And so again, we begin by looking at the equation. So if we look at this first example, f of x equals 2x plus 3. Okay, I look at it. Again, my initial assumption is that my domain is all real numbers. And I'm going to think about my restrictions. I don't have a fraction. This is not a rational function, so I don't have to worry about dividing by 0. Nor does this example have a radical, so I don't have to worry about that. So by default, then, the domain of this function is negative infinity to positive infinity. Now, to support that contention, you can go out and perhaps create a picture, or you can recognize that that is a line or a linear function, and that a line is always going to have the domain of all real numbers. And I'm trying to pull my calculator up here. It's just taking it a little bit of time. While we're waiting on it to come up, we can look at the second one. Okay, so for the second example, we have f of x equals x squared minus 1. Again, my initial assumption is that the domain is all real numbers, negative infinity to positive infinity. Again, looking at this function, it does not contain a radical, nor does it have a fraction. Okay, doesn't have a fractional exponent so that I have a numerator and a denominator. So again, by default, my domain is going to be negative infinity to positive infinity, or all real numbers. And again, you can verify that by creating the graph of the function. So let me go back for just a minute and graph the first one. We had 2x plus 3. So if I go up to my graphing functions and say y equals 2x, was it plus or minus 3? Plus 3, plus 3, and then I have it graph. Hopefully visually you see that that's a line, and by definition a line keeps going on forever ever in both directions. Visually there's no holes or breaks or gaps in the function. We can also do that for the second one that we were just looking at, the x squared minus 1. Okay, so we do x squared minus 1, and we graph it. Okay, and again, if you'll notice, and it's not as, perhaps maybe not as obvious to you, but there are, technically this graph goes on and on and on and on forever, up on the left and up on the right forever and ever. And as it goes up, it continues to move out. So again, my domain, there's no holes or gaps or breaks. So my domain is all real numbers. Looking at the third example here, we have 1/2 times x minus 2. So again, we begin by assuming that my domain is all real numbers. And you may think, well, Miss Ralston, that one's got a fraction in it. Well, yes, it does, but the fraction does not have a variable in the denominator. And since the variable is kind of beside it, it's not in the denominator, it's a multiplication, then I don't have to worry about having division by 0. Now, if you want to contrast that, if you look at the next example where we have 1 over 2 minus x, notice now that that x is definitely in the denominator or in the bottom half of the fraction. Okay, so for the third example, 1/2 x minus 2, again, I don't have a radical and there's no variable in the denominator, so again, my domain is all real numbers. And again, you can verify that if you want to. You can plug it into your calculator. I can do, let's see, 1 divided by 2. I put my fraction in parentheses, times x minus 2. And I graph it, and again, visually, you should get a line, and again, we know that a line goes forever, ever in both directions. So it may help you when you're making these decisions to look at the graph, and I'll show you even with some of these where there are restrictions. So on the fourth example here, it is a rational function. It's what we call a rational function because it looks like a fraction. And since it's a rational function, I have a numerator, which in this case is 1, and I have a denominator, which is 2 minus x. Now, in the definition of a rational function, the denominator can never, ever equal 0 because division by 0 is not mathematically possible. So in this case, I know there's going to be a restriction. And the way we determine what the restriction is we take the denominator and say it cannot be 0. So for this particular problem, I would have 2 minus x cannot be 0. And then I have to solve that basic algebra equation for x. So I'm going to add x to either side of the equation, and I get 2 cannot equal x. So in this case, x cannot be 2. So I can use any number on the number line that I can think of except 2. Now, in terms of interval notation, here's what you would write. It may help you to think about it on a number line so you can see it visually first. Okay. We're saying that we cannot use a value of 2. So it's like there's this big old hole in the number line at 2, but I can use anything to the left and anything to the right. I just cannot use 2 because I don't want to fall in the hole. So my domain would be from negative infinity all the way up to 2, and then I'm going to step over the hole and continue on from the other side of 2 to positive infinity. In words, we would say it's all real numbers except positive 2. Moving on to the fifth example, again, in this particular problem, I have a rational function because it looks like a fraction. And again, I have to be sure that when I have a fraction, that the denominator of the fraction cannot be 0. So again, I'm going to take the denominator, which is 2x minus 1, and say that it cannot be 0. And then I'm going to solve that basic algebra equation. I'm going to add 1 to either side. So we have 2x cannot be 1. Then we're going to divide both sides by 2. So x cannot be positive 1/2. Now again, visually, if you want to picture that on a number line, okay, you can estimate where 1/2 maybe falls on the number line. Okay, so we would have this big old hole at 1/2. And again, we can choose any value to the left or any value to the right. So in terms of the domain, we would have from negative infinity to 1/2, step over the hole, and we're going to go from 1/2 to positive infinity. And then I want to look at one more, because sometimes if the denominator is more of, in this case, like a quadratic or a cube or something else, you may have to use factoring or some other technique. But again, the restriction still holds. This again is a rational function because it looks like a fraction. So we still have the restriction. And again, the restriction is that the denominator cannot be 0. So in this particular case, we have negative 30x squared minus 25x plus 5, and that cannot equal 0. Now, typically with a quadratic, there's a couple of ways to solve it. You can do factoring or use the quadratic formula. I'm going to use factoring, and the first thing I notice is that all of these numbers can be divided by 5, and I'm not fond of the negative, so I'm going to factor out a negative 5. So negative 30 divided by negative 5 is 6x squared. Negative 25 divided by negative 5 is positive 5x. Positive 5 divided by negative 5 is negative 1, and that cannot be 0. I still need to continue my factoring, so I have the negative 5, and then I'm going to break down the quadratic inside. I tend to do it trial and error. I know the two numbers that multiply to 1 is 1 and 1. I need a pair of numbers that will multiply to 6 but subtract to 5. So that's going to be 6x and 1x, and I want a positive 5, so it becomes negative 5 times 6x minus 1 times x plus 1. And we know one of those pieces had to be 0. Well, -5 does not equal 0. That's a true statement, and that'll always be true. So then I have to figure out 6x minus 1 cannot be 0, nor can x plus 1. It cannot be 0 either. And so then I'm going to solve each of those individually for x. I'm going to start with x plus 1. It really doesn't matter. So I subtract 1 from either side. So we find that x cannot be -1. So there's one restriction. Then on 6x minus 1, I'm going to add 1 to either side. So I have 6x equals 1. Then I'm going to divide both sides by 6. So I have x equals 1/6. So for this particular function, I actually have two different restrictions. Okay, so again, if you think about it on a number line, you're going to have a restriction at -1, and then you're also going to have a restriction at +1/6. So there's a big old hole at -1, and there's a big old hole at 1/6. But again, you can use anything to the left, anything to the right, and anything in between those two numbers. So ultimately, my domain goes from -infinity to -1, step over the hole, from -1 to +1/6, step over the hole, from +1/6 to +infinity. Okay, so let's move on to some examples where we have radicals. In this next example, we have the function is the square root of 7 minus x. Okay, so this is a square root function. The square root is an even indexed root. So we have to assure that this number underneath, which is called the radicand, is greater than or equal to 0, which means it's got to be positive. So in this case, I do have to worry about the restriction, and the restriction is that the radicand must be 0 or positive. So the way we decide what our restriction is going to be is we take the radicand, which in this case is 7 minus x, and we say it's greater than or equal to 0. And then you solve that inequality. Now again, you have to be careful and remember the process. So I'm going to subtract 7 from either side. So I have -x is greater than or equal to -7. Then I'm going to divide both sides by the -1. Now here's where you have to remember some algebra rules. The algebra rule says when you multiply or divide an inequality by a negative number, you have to flip it. So it becomes x is less than or equal to +7. And again, it may help you to see that visually on a number line. So on a number line here, we would have a closed dot, because it's equal to, it could actually equal 7. So you have a dot at 7 and it's colored in, and it's going to be less, and values that are less go to the left. So I could use numbers like 6, 5, 4, 3, and so forth. So in terms of interval notation, we would have from -infinity to 7, and the 7's included, so we use a square bracket. Okay. The next one, we have, again, it's a function. It's a radical. Again, you could see this. I didn't show it to you on a graph. I can try to go back and show it to you in just a minute. But if you take the square root of -5x plus 20, again, we know we're going to have the restriction because I have an even index radical, I know I'm going to have the restriction that the radicand must be 0 or positive. So again, I'm going to take the expression that is under the radical, which is negative 5x plus 20, that's greater than or equal to 0. And again, I need to solve that for 0. So to do that, again, I would subtract 20. I'm going to isolate the x, good old basic algebra. So I have negative 5x is greater than or equal to negative 20. I'm going to divide both sides by negative 5. Again, since I'm dividing by negative, I have to flip the inequality symbol, so I have x is less than or equal to positive 4. Again, that may help you to visualize that on the number line. Okay, so you again would have an dot at 4, and it would be colored in because it's equal to, and then again it is less than. So in terms of your interval, we go from smallest, which is negative infinity, to largest, which is 4, and it's usable, so we put a bracket at the 4. Now sometimes they can get real interesting because you can have an example similar to this last one where you have both a rational function, so you have a fraction, and you have a radical in that fraction. So in this case, you have to deal with both restrictions. Okay, so that means that the denominator cannot be 0, and then that basically means your radicand must be positive. You can no longer say that your radicand is 0 because it can't be 0. So you have to fit in both restrictions. So we would have 4x minus 12, which is our radicand, is greater than 0. It can no longer be equal to 0. So we leave that part of it off. And again, you solve it, good old basic algebra, add 12 to either side. So 4x is greater than 12. And then we're going to divide both sides by 4. I don't have to flip the inequality this time because I didn't divide or multiply by negative. So x is greater than 3. Again, thinking about it in terms of the number line, so we can write it in interval notation. In this case, you would have an open dot at 3 because you can't use 3, and you want to be greater than, which is to the right. So ultimately, our domain begins at 3, and it's a parenthesis because we're not using the 3, and it keeps going to positive infinity. So I hope you find this video helpful in learning how to find the domain of a function when you're given the equation.